our schedule here indicates that we should proceed to the second talk by Professor Ching-Ming. Hello, Professor Ching-Ming.
Yes, I will share my screen.
All right, then now you have the opportunity to present your talk, and I kindly remind that the time allocated for the talk is just 20 minutes. I'm sorry to say that, but now is the time is yours, Professor Wei. Please.
So should I start?
Yes. Yes.
Okay. Okay. First of all, I would like to thank the organizing committee to give me a chance to introduce our recent work. That is the exploring different dynamics of superionic material using machine learning into atomic potentials. In this talk, I will show you how powerful our computer can help in the material researches. Okay. And I'm Ching-Ming from Institute of Atomic and Molecular Sciences at Taiwan. Okay. The work was done by Dr. Ching-Ming and Dr. Durong. Okay. And before that, I will introduce a so-called Taiwan International Graduate Program, which in our institute we have the Molecular Science Technology Program. Okay. And here are the IP address. And this program is an excellent research intensive interdisciplinary PhD program sponsored by our institute and also 3 neighboring universities. That's National Taiwan University, and National Tsinghua University, and the National Central University. So if you are interested in this program, please go back, look into the details. Okay. Now let me start with the introducing what are superionic materials. Superionic material are material with some of its mobile atoms like copper, silver, and zinc, diffuse freely inside the framework formed by the other atoms such as sulfur, tellurine, and tellurine. Okay, so this kind of material basically is kind of liquid-like thermoelectric material. Okay, this liquid-like behavior of copper or silver ions around the crystal sublattice result in the ultra-low lattice thermoconductivity. The reason is that because phonon can be suppressed by liquid-like behavior of the copper or silver. Okay, so here I show some kind of different materials lattice thermoconductivity. They are pretty low, which will very have a good application in the thermoelectric materials. Okay, which will give a high figure merit. Okay. And so here are type of the copper to sulfur, silver, sulfur, or copper, silver based iodide material. It's A16 material. Okay, and of course, sometimes these ion battery material are also called superionic material. However, we have to notice that the lithium ion are fixed at the lattice side. However, they do have a kind of frankly hopping effect. Okay, I will show you later by simulation. Okay, let me start with the one of the sample of the A16 materials. Okay, and you can see that that is some kind of very low. Okay, and to determine to study this kind of material, of course, first we would like to obtain the structural information experimentally. Okay, we know that get the structural information experimentally, one need to use the X-ray powder diffraction or X-ray single diffraction to obtain the structural information. And the way of doing this kind of method is that by guessing an initial structure to simulate its diffraction pattern and compare to the experimental measurement. If it fits well, then we believe the structure is correct. If not, then we will repeat again to guess the structure and repeat it again. Okay. So basically, this kind of XRD fit deformation is the trial and error process, and which is very difficult for complicated system. For example, here we have the A16 iodide materials, and there's the powder diffraction pattern at the different temperatures. Okay, and then you can simulate the diffraction pattern. Okay, here Fi is the atomic scattering factor, and J is the assigned occupation numbers. Okay, and actually from this group, Hui Yangzhong's group, my colleague there, they have finally got out this kind of structure models. Okay. And the structure model can summarize like this kind of so-called 4 AGKGs model. Okay, so here you can have AGKG here, 4 AGKG, and each KG they have the double shell. And here the characteristic structure is a triangular and the square. Okay, so however, for this kind of requirement, they took actually more than 1 year to finish the fittings. Okay, however, you go back to the literature search to find the similar structure, you will find that actually most of the this kind of A16 system, they have a different partial occupancy for the silver atoms. For example, 1, 2, 3, 4. They are very different. And actually, it's very difficult to judge which one is correct. Okay, so I will say structural prediction with partial occupancy from SRD is not suitable for this kind of super ionic material, where you have some kind of mobile atom to move in inside the framework of other atoms. Okay, so we actually developed some method to define this kind of system using the molecular dynamic simulations. Okay, we define the so-called 3-dimensional atomic density distribution function for the crystal. Okay, so based on that, we need something useful to fit the SRD or even beyond. Okay, as we all know that the molecular dynamic simulation actually is doing quadratic measures in SRD. Okay, it's a time average of the material system that we expect that the average structure of the molecular isolation will give very useful, give the average structure of the material system and a good starting for X-ray RD fitting. Okay, so for example, here we show one case of the MD simulation to get the 3D atomic density distribution function and compared to the experiment. Okay, you see there's very similar similarities. Okay, indicate both methods are right. Okay, and so now how we do this kind of MD simulation to get atomic density distribution function. Okay, we'll start using the experimental suggested constant and crystal symmetry. Okay, like this one A16 here, we have the framework like this, and then we use the so-called random search method to generate initial position inside this framework. Okay, and then we do the DFT calculation to get optimized structure. Okay, and then without symmetry, and then we get the 6 lowest any structure perform MD simulation the different temperatures. Now here are the results. For example, we have the 6 initial structure, and after the 400 picosecond the MD simulation, we get the AD trajectory to form the atomic density distribution function, and they are very similar. Okay, and for silicon and telluride, the atoms are just moved around the local position without the diffusions. Okay, in other cases, this is give a more clear pictures. And now, if we have a lower temperature simulation at 300K, here are the 300K, because the silver do not get enough kinetic energy to do the diffusions. So different initial configuration do not really give a similar patterns. However, by summing all 10 initial structures, we get the pattern, which is very similar to the high energy patterns. Okay, so these are how we get this kind of 3 atomic density pattern, and these are the property or material properties. Okay, and so here are cases 300 and 600K, and you can clearly see that this pattern is temperature dependent. Okay, and then we use this data compared with the experimental fitting result. Okay, which give us a very good agreement, as you can see here. And so for this case, you already showed that MD simulation and for some long times, and then you put all the atom into the conventional primary unit cell, then you will give it a 3D atomic density distribution pattern, which will give you the very clear structural nature of the system. Okay, now let's go to the second case. If I will describe for the copper-sulfur system. Here for copper-to-sulfur, we have a hexagonal structure and also FC structure. And if you go to the literature to search the final result for the copper-to-sulfur and the FCC structures, and you will see actually they have 9 fitting of the different structures, and which frankly speaking, we cannot trust anyone is correct one. Okay, so by doing the MD simulation, you can see the copper is moving around all over the crystal, the framework of the sulfur atoms. Okay, and if you do the low mean square displacement, you will see the straight line, and this straight line give you the diffusion constant, and if you have the temperature dependent diffusion constant, you can get the diffusion barrier. Okay, by Arrhenius equation. However, if you look this one, so-called hexagonal closed packed copper-2 sulfur system, you can see the low mean square displacement is not a straight line, and which means that it's not converging yet. And why they publish the paper? Because they have not enough computing time to do the full complete studies. Okay. So we also do the same simulations and be passionately to do the MD simulation. And this is the FCE system, and you can see the 3D atomic density diffusion function of 10. Okay, and for the hexagonal closed pack, okay, it's mostly interesting by summing only copper atom inside a primitive unit cell or one by one unit cell. And you can see here these are the sulfur atom, the sulfur atom. This is the framework. Okay. However, you can see the copper atom isolated here, and here are also the copper atom, but there is a diffuse triangular, and this triangular and low triangular, they actually have the channel from this side upside to the low side. Okay, and you plot out 2x2 one symmetry, and you can see that, and use copper low density, you will actually see this kind of constant surface will actually make out the possible diffusion path for the copper atoms. Okay. So the summary, the first part is the maximum point of three-dimensional atomic density diffusion function. Okay, obtained from MD simulation can use as a starting point for partial occupation prediction for X-ray fitting, or also the connected 3D atomic density diffusion function clearly indicate and define the diffusion path inside the crystal. Actually, there is also possibility, for example, here. Experimental suggest a symmetry for this copper-2 sulfur hexagonal pack is the P363 symmetry. However, MD simulation actually point out is actually not that high symmetry. It's just a P331 symmetry. Okay, so actually this MD simulation tell us the experimental assignment symmetry is actually wrong. Okay, to indicate its powerfulness. Okay, of course, based all kinds of things are the first principle simulation by density function. And you all know that the density function is so expensive, and in fact that means if we would like to do the density function MD simulation, which is so expensive, and the system we can handle is too small to study. Okay, and so for example, we have a partial occupancy or superharmonic system, or we have some kind of disorder system, or with the vacuum and the doping, or the complex system. The first things for dynamic simulation are too expensive to perform. Okay, and one need to use so-called machine learning interpreting potentials. Okay, the idea of this machine learning interpreting potential is that you started to do the Benioff simulation maybe 5,000 times that. Then you can get each configurations. You have the total energy and forces on each atom, and also the strength of the system. Okay, to use this kind of information as input data, then you train your potentials. Okay, and you obtain the machine learning intermittent potentials, and then you go to test another set. Okay, the test set, train set other training, and you go to the test set. And if the train test and test set, they obtain the very reasonable mean square displacement of the forces, then you think the potential will be good. Okay, then you get the final MD potentials, and you can search for new structure or calculating the material property. And we use this kind of so-called MD package. Okay, a moment tensor with the MPI, and this is very powerful technique. And so I will show you an example later. Okay, yeah. So before that, because we're doing the diffusion dynamics, so we need the so-called Arrhenius equation to study diffusion behavior. Okay, the idea is that this diffusion rate or constant, diffusion constant, will be a prefactor, and its potential EA divided by 1 over K divided by KBT. Okay, so if you take a log, you will see that the diffusion constant as a function of temperature will equal to some kind of constant minus the EA divided by KBT. So if you plot the dt versus the 1 over T, then you will get a straight line, which will give the diffusion barrier of the EA. Okay, so this is the idea, and I will show you later here. There's A16 or carbon side HCP over. We all get the straight line. Okay, here we have mean square displacement. Okay, as a function of picosecond. Okay, and you can get the diffusion constant. Okay, that means the result already converged for these calculations. Okay, and now let me show you the first case superionic crystals. And for IAC2 sulfur, and we this again, the experimental field structure are not agreement each other, and to the perfect principle and molecular insulation, we can get better nice result. However, we can use MDIP to fit the machinery interacting potentials. And here are the original data. We have 162 atoms and for 10,000 steps, and then the average force is something like 0.963 EV per angstrom. Okay. However, after the fitting, we know the average absolute difference is only 34 MeV. So the error in force is only 3.5 things. Okay. And so we can do the simulations. Okay. And for example, here I show the 750 case. You can see that the 3D atomic density diffusion pattern are very nice and very beautiful. And if you plot out the diffusion constant as a function of the 1 over T, and you can see the very straight line here. And the diffusion barrier is 93 MeV. Okay. And so of course we would like to study dynamic behavior. So we plot out the mean square displacement length distribution for different temperature, like here 450 to 800 K. And you can see that they are not merged to each other, and you really cannot dig out much information there. Okay, so we think that for this system, and the particular temperature, particular diffusion time, okay, the characteristic length is the so-called root mean square displacement. So we normalize to this root mean square displacement, okay, and then you will find that all the curves are merged together. This means the system already reached the equilibrium at least 250 picoseconds, and then we try to see the allocation. For example, this A16 system, okay, and the atomic density pattern are completely similar, and this indicate the experimental model and our MD and molecular model are close enough. Okay. And again, you can see the barrier is roughly 105, 100 MeV, and here, okay. And actually, for this energy range, temperature range, the diffusion constant is this value. And you look at this value, actually, it means that in one day, the silver atom can move 1 centimeter. So you can see how you move fast of these kind of superionic materials, okay? And then here are the results from the copper to sulfur for SCP and for FCC, and the diffusion barrier also 150 something, okay? So the diffusion barrier is straight line and give you the barrier of 150 something, okay? I mean, you study the root mean square displacement length, okay? In terms of the root mean square displacement length, okay, and then everything merged together. Okay, this is for FCC crystal. However, if you go to study SCP copper to sulfur, you will see something strange here. That means all the atoms here are not moved yet. Okay, not joined the diffusion yet. Okay, so this is not converged. And then if you go to see the different temperature and then at the 240 picosecond here, and then because they are not moved, so yet. So we try to increase the diffusion time for level 480, and this becomes smooth. It becomes smaller. The most atom join, most of the color join the diffusion, and finally we go to the 9.6, only 1 nanosecond, and then the blue curve indicate everything was join the diffusion event. So, however, you see the 1 nanosecond indicate actually this kind of thing is untouchable by density function zero. So we really need this kind of machine learning approach. For example, this case we have calculated the machine learning for 5 nanoseconds, and you see with here everything was already converged. Okay, so simulation time for nanosecond easily achieved by this kind of machine learning interleaving potential, and for the DFT, 100 picosecond is already basically the limit. Okay. Okay, so let me start talk about the lithium ion lithium materials. Okay, lithium ion battery material. There's one case we study. For this case, it's basically the lithium ion diffuse only 2 dimensions only. Okay, it's a daytime material. Okay, this X indicate the lithium and the vacancies. Okay, for equal 1 is all the vacancy. There is no vacancy. For little is there is no lithium. Okay, and I would like to address a little bit later. The project was done by Lily from Matara and Dr. Shinjano in my group. Okay. So the quality of this interleaving potential, we can see actually now is much accurate, only 2% accuracy. Oh no, 2% of error is very 9% accurate in the atomic potentials. Okay. So if you do this kind of simulation at 700K, you will see plot the atomic density diffusion function. You can see that these things are actually moved 2-dimensionally. Okay, however, for copper and oxygen, they are actually do not only vibrate at the equilibrium positions. Okay, so that indicate the lithium ion diffuse 2-dimension only, and that's what a single cell absorption, and either the lithium side or vacancy side. And you barrier, okay, barrier is something 200 MeV, and you plot the root mean square displacement at 500 picosecond. At different temperature, you can see it's basically the hopping distance, diffusion distance always very discrete. That means this really so-called static side hopping mechanism. Okay, and of course one would like to understand what kind of this kind of hop side mechanism will be smeared out after some time, maybe 20 nanoseconds. However, these are results for simulation of 20 seconds. Still, is kind of not merged to one. There's very sharp this kind of spike, but it is still a side hopping mechanism. It's not smeared out by the simulation time. Okay, so simulation time for this kind 20 seconds is achieved by machine learning interleaving potential, and 2D side hopping feature still remain after 20 nanoseconds. Of course, one may ask how powerful this kind of machine learning approach is. And before I conclude my talk, I will show you one case. This is the okay, 2 minutes.
Yeah,
okay, thank you.
Yeah.
So this is the super ionic core in the our Earth. Okay, so they found that the hydrogen, copper, oxygen inner core, there is convention within this high pressure. Okay, and they are doing the DFT calculations, and they with only very small ion and 64 ion and copper and oxygen, and so you see that the root mean square difference is not a straight line, so indicate not converge. So can we do this kind of machine learning approach to study system? Of course, the answer is yes, clearly. And here are the results. I will show you that. See, we have more than 5,000 atoms are in the simulation using this approach, which is actually the number of atoms is 64 times larger, and at 7,000 K and 630 gigapascals. And you can see the root mean square development is complete straight line, indicate this is very nice, and the results converge. Okay, and you can see that within this range, they have the straight line diffusion constant as the 1/T, and we can get the copper, oxygen, and hydrogen, and all the diffusion barrier. Okay. So the technical issue is the machine learning interlearning potential second only 2 or 3 for force accuracy can actually speed up the molecular dynamic simulation by a factor of 10 to 5 or 10 to 6 compared to the very costly density function theory calculation. So the other thing is that the machine learning interlearning potential is perhaps the only way to probe dynamic behavior for super-ionic material. And thank you for your attention and waiting for the question or comment. Thank you.
Thank you, Professor Wei. The challenge for the study of super-ionic materials, the structural characterization challenges from the experiment like XLP to molecular dynamics simulation, and using the approach of machine learning in the atomic potential. Thank you.
Okay.
Ladies and gentlemen,